For over 1,000 years, humanity looked at the stars and believed we were the center of everything. The earth stood still. The heavens revolved around us. It was written in ancient texts, preached from pulpits, and taught in every university. And then a few men with telescopes, mathematics, and dangerous ideas shattered that cosmic illusion forever. This is the story of how we learn to see the universe as it truly is, and how that knowledge nearly destroyed the men who discovered it. Imagine living in a world where everything you believed about reality was wrong. Not just slightly off, but fundamentally, catastrophically incorrect. That was Europe in the early 1500s. For nearly 2,000 years, the Western world had been living inside a cosmic story written by ancient Greeks. Aristotle had declared that Earth sat motionless at the center of the universe. Around it, the moon, sun, planets, and stars rotated in perfect crystalline spheres. Everything up there moved in flawless circles because circles were perfect. This wasn't just science. It was theology, philosophy, and common sense all wrapped together. The Catholic Church had adopted this view completely. To question it wasn't just wrong, it was heresy. Universities across Europe taught Ptolemaic astronomy, a complex mathematical system developed by the Greek astronomer Ptolemy around 150 AD. It predicted planetary movements using elaborate models of circles within circles called epicycles. It was accurate enough for navigation and calendars, so why question it? But there were cracks in the cosmic dome. Astronomers had noticed problems. Mars didn't quite move where the model said it should. Venus showed phases that didn't make sense if everything orbited Earth. These were small annoyances that required increasingly convoluted explanations. The system was becoming absurdly complicated, with dozens of invisible circles needed to explain what the naked eye could see. Then, in 1543, as he lay dying in Poland, a church administrator named Nicholas Copernicus published a book that would ignite a revolution. Copernicus wasn't a rebel. He was a cautious man who had waited decades to publish his ideas. But his mathematics had led him to a radical conclusion. What if the sun, not Earth, was at the center? What if our planet was just another wanderer spinning through space? His book, De Revolutionibus Orbium Coelestium, presented the heliocentric model, a sun-centered cosmos where Earth rotated on its axis and orbited the sun along with the other planets. The elegance was stunning. Suddenly, the strange backwards motion of Mars made sense. The phases of Venus became obvious. You didn't need all those epicycles anymore, but elegance doesn't win arguments against centuries of tradition. Most scholars dismissed Copernicus immediately. Some mocked him. The Protestant reformer Martin Luther called him a fool who wanted to turn all of astronomy upside down. The Catholic Church initially tolerated the book as mathematical speculation, not physical reality. After all, it was absurd to think Earth was spinning. Wouldn't we feel it? Wouldn't birds get left behind when they jumped into the air? Wouldn't everything fly off into space? These weren't stupid questions. They were legitimate concerns that exposed a deeper problem. Nobody understood motion yet. Nobody grasped inertia or gravity. The physics needed to support Copernicus didn't exist. For decades, the heliocentric theory remained a curiosity, a mathematical trick that a few astronomers found useful, but that most educated people rejected. The world continued to believe it stood still at the center of creation. But across Europe, a new generation was growing up. They had inherited not just Copernicus's mathematics, but something more dangerous: permission to question everything. The idea had been planted that perhaps the ancients were wrong. Perhaps observation and calculation mattered more than authority and tradition. The revolution had begun, but it would take telescopes, persecution, and the work of minds more brilliant and reckless than Copernicus to complete what he had started. And the price for disturbing humanity's cosmic self-image would be paid in house arrests, burned bodies, and intellectual warfare that would rage for over a century. In November 1572, a Danish nobleman named Tycho Brahe looked up and saw something that shouldn't exist. A new star had appeared in the constellation Cassiopeia. Brilliant, blazing, impossible. According to Aristotle, the heavens were eternal and unchanging. Stars didn't just appear, but there it was, visible even in daylight for weeks, a cosmic announcement that the old certainties were crumbling. Tycho became obsessed. He built the finest observatory in Europe on a private island and spent decades making the most precise astronomical measurements the world had ever seen. He mapped the positions of over 1,000 stars with his naked eye alone. No telescope existed yet, just brass instruments, mathematical genius, and relentless patience. But Tycho couldn't make sense of his own data. He rejected Copernicus's sun-centered model. It seemed too radical. Instead, he proposed a compromise where planets orbited the sun, but the sun orbited Earth. It satisfied no one and solved nothing. When Tycho died in 1601, his assistant inherited those decades of observations. His name was Johannes Kepler, and he was a mathematician who believed God had written the universe in the language of numbers. Kepler dove into Tycho's data on Mars, expecting to find the planet moving in perfect circles, as everyone assumed. Instead, he found chaos. For years, Kepler wrestled with the numbers. He tried hundreds of circular orbits. None worked. The observations refused to cooperate. Finally, in an act of mathematical desperation, he abandoned circles entirely and tried something scandalous: ellipses, ovals, imperfect shapes. And suddenly, everything clicked. Mars wasn't moving in circles. It was tracing an elliptical path with the sun at one focus. When Kepler applied this to other planets, the patterns emerged like magic. He published his first 2 laws of planetary motion in 1609, showing that planets moved in ellipses and swept out equal areas in equal times. Later, he added a 3rd law connecting orbital period to distance from the sun. For the first time in human history, someone had described how the heavens actually moved, not how they should move according to ancient philosophy. But while Kepler was crunching numbers in Prague, an Italian mathematician was about to show the world what the heavens actually looked like. Galileo Galilei had heard rumors of a Dutch invention, lenses arranged in a tube that made distant objects appear closer. Within months, he had built his own version and done something no one had thought to do. He pointed it at the sky. What Galileo saw in 1609 destroyed the ancient worldview completely. The moon wasn't a perfect sphere. It had mountains and craters, rough and scarred like Earth. The sun had spots, dark blemishes that moved across its surface. It wasn't divine and flawless. It was a physical object that rotated. Then he turned his telescope to Jupiter and watched, night after night, as 4 tiny points of light danced around the planet. They were moons. Jupiter had its own miniature solar system. If moons could orbit Jupiter, why couldn't planets orbit the sun? He looked at Venus and saw it showing phases exactly like our moon, sometimes a crescent, sometimes nearly full. This was only possible if Venus orbited the sun, not Earth. The evidence was now visible. You didn't need faith or philosophy. You could just look. Galileo published his discoveries in Sidereus Nuncius, the Starry Messenger, in 1610. It became an instant sensation. Printed books carried his findings across Europe within months. For the first time, the printing press allowed a scientific discovery to spread faster than the church could suppress it. The universe had been blown open, and the authorities were about to push back. Galileo made a fatal mistake. He didn't just present evidence, he mocked those who disagreed with him. In 1632, he published Dialogue Concerning the Two Chief World Systems, a conversation between 3 characters debating geocentric versus heliocentric models. One character, Simplicio, defended the Earth-centered view with arguments that sounded suspiciously like those made by Pope Urban VIII himself. The Pope had been Galileo's friend. Not anymore. The Inquisition summoned Galileo to Rome. He was 70 years old, in failing health, and facing an institution that had burned the philosopher Giordano Bruno at the stake just 3 decades earlier for suggesting the universe was infinite. Bruno had died screaming in 1600. The message was clear: some ideas were worth killing for. Galileo was given a choice: recant or face torture and execution. On June 22, 1633, kneeling before the cardinals, he read a prepared statement. He declared that he abjured, cursed, and detested the heliocentric theory. He admitted his errors. He swore the earth stood still. Legend says that as he rose to his feet, he muttered under his breath, "Eppur si muove," and yet it moves. Probably not true, but it should be. He spent his final 9 years under house arrest, forbidden from publishing, his dialogue added to the Index of Forbidden Books. He died in 1642, blind and isolated, never having seen his ideas accepted. But here's what the Church couldn't suppress: the method. While Galileo was being silenced, other men across Europe were establishing a new way of understanding reality. Not through ancient texts or religious authority, but through observation, measurement, and experiment. In England, Francis Bacon was writing manifestos for this new approach. His Novum Organum, published in 1620, laid out a systematic process. Gather data, look for patterns, test hypotheses, draw conclusions. Start with observations, not assumptions. Let nature speak for itself. This inductive method, building knowledge from evidence upward, was revolutionary. For 2,000 years, scholars had worked the opposite way, starting with ancient authorities and deducing downward. Across the Channel in France, René Descartes was approaching the same problem from a different angle. Doubt everything, he argued, until you reach something you cannot doubt. Then use logic and mathematics to build outward from that foundation. His famous declaration, "I think, therefore I am," established that the thinking self was the only undeniable starting point. From there, apply reason like a mathematical proof. Descartes saw the universe as a giant machine obeying mathematical laws. Understand the math, understand the machine. Two different paths, Bacon's empiricism and Descartes' rationalism. But both agreed on something radical. Human beings could figure out how nature worked without consulting ancient books. We didn't need Aristotle's permission. We needed eyes, instruments, and minds willing to challenge everything. And the tools were getting better. Microscopes revealed a hidden universe of bacteria and cells. Barometers measured atmospheric pressure, proving air had weight. Vacuum pumps showed that space could exist with nothing in it, contradicting ancient claims that nature abhors a vacuum. Robert Boyle was conducting careful experiments on gases, discovering mathematical relationships between pressure and volume. William Harvey was dissecting cadavers and proving that blood circulated continuously through the body, powered by the heart as a mechanical pump. Science was becoming collaborative. The Royal Society of London, founded in 1660, created a space where natural philosophers could share discoveries, debate findings, and build on each other's work. They published the world's first scientific journal, establishing peer review and intellectual credit. Ideas were no longer locked in private notebooks. They were public, testable, and improvable. The revolution was spreading, but it needed one final architect to tie everything together into a complete system. And in 1642, the same year Galileo died, that architect was born in a small English village. His name was Isaac Newton. Isaac Newton was born prematurely on Christmas Day, so small his mother said he could fit inside a quart mug. No one expected him to survive. He did more than survive. He became the mind that would finally explain why Copernicus and Kepler were right. Newton was strange, obsessive, and solitary. He worked in bursts of manic intensity, forgetting to eat or sleep, scribbling equations that no one else could understand. In 1665, when plague closed Cambridge University, he retreated to his family farm and spent 18 months in isolation, having what might be the most productive intellectual episode in human history. During those months, he invented calculus, the mathematics of change that let you calculate motion with precision. He discovered that white light was actually composed of all the colors of the rainbow, which he proved by passing sunlight through a prism. And he began working on the problem that would define his legacy. Why do things fall? The famous apple story is probably embellished, but the question was real. Why does an apple fall down? And more puzzling, why does the moon not fall down? It's moving around Earth, clearly being pulled toward us, but it never crashes. What keeps it up there? Newton's answer was almost insultingly simple. The moon is falling. It's constantly falling toward Earth, but it's also moving forward so fast that it keeps missing. It falls around us in an endless circle. The same force pulling the apple to the ground is pulling the moon into orbit. Gravity isn't just an earthly phenomenon, it's universal. This was the breakthrough that unified physics. For centuries, philosophers had insisted that the heavens operated by different rules than Earth. Earthly objects were corrupt and moved according to different principles. Newton proved this was nonsense. One law governed everything. In 1687, he published Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. The Principia is one of the most important books ever written. In it, Newton laid out his 3 laws of motion and the law of universal gravitation. Every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. From this single equation, you could predict the orbit of planets, the arc of a cannonball, the trajectory of a comet. Kepler's ellipses weren't mysterious anymore. They were the inevitable result of gravity. Galileo's observations of falling objects fit perfectly. Copernicus's sun-centered system was now backed by mathematical proof, so solid you couldn't argue with it unless you rejected mathematics itself. The scientific revolution was complete. In less than 150 years, humanity had gone from believing Earth was the motionless center of creation to understanding that we were spinning through space on a planet governed by the same mechanical laws as everything else in the cosmos. We weren't special. We weren't central. We were just another rock orbiting an ordinary star. This new worldview changed everything. If the universe operated like a machine following mathematical laws, then maybe everything could be understood through reason and observation. This confidence sparked the Enlightenment, inspired political revolutions, and eventually led to the Industrial Revolution. The idea that humans could master nature through science became the driving force of modernity. But it came at a cost. We had gained knowledge and lost our cosmic significance. We understood the machinery, but had trouble finding meaning in it. The questions the scientific revolution answered: how do the planets move? What makes things fall? Were replaced by harder ones. Why are we here? What does any of this mean? Those questions remain unanswered. But at least now we know how to ask them while standing on a spinning ball of rock, hurtling through the void at 67,000 miles per hour. Held in place by invisible forces, we've learned to measure, but still struggle to truly comprehend. The revolution didn't just change what we knew, it changed what it means to know anything at all.